Hey everybody, welcome to Altium Academy. I'm your host, Zach Peterson, and today we're going to be going over how to design a USB to UART bridge converter, and we're going to use the CP2102 chip from Silicon Labs. I've been having a problem with the USB to UART converters that I purchase online. They usually come in 3-packs, and they come in 3-packs for a reason. It's because they will fail pretty easily, and they're very susceptible to ESD, which is pretty unfortunate because I've run through a couple of packs of these already. So since I'm getting tired of having to buy USB to UART converters all the time on Amazon, I'm gonna make my own, and I'm gonna show you how to do it in Altium Designer. So make sure to hop into Altium Designer, follow along, and let's get started. So this is what we're going to be working with. This is a USB to UART bridge converter, and we're going to design one of these custom in Altium Designer. Now, this has a pretty simple function. It basically provides an interface to a USB port on your computer. It allows the USB port to receive a data stream over a UART interface. So the UART interface is built into this chip. This is the CP2102. There are variants of the CP2102 that you can also use for this. It also puts out a couple of voltages here. So if we just plug this guy in, we can take a couple of measurements here and see what it's actually outputting. If you just hook up the multimeter and just take a couple of measurements, the first one that you'll see here is we have a 5-volt measurement. So you can see that here on the multimeter. So it's about 5.16 volts. This is the standard bus voltage coming through the USB connector. And if you look on the back of this board, you'll actually be able to see a trace running from the power pin on this USB connector over to this other pin on the pin header. Now, this chip also outputs a 3v3 voltage. So if you just reverse these connections just a little bit, bring this over here, see that it also outputs at 3.4 volts. So there is a regulator in this module that is converting that 5-volt bus voltage coming through the USB connector down to 3 volts. So if you actually look on this board, you would want to look for a regulator circuit, right? Well, you actually won't see one, and that's because the CP2102 has a built-in regulator that will convert that 5 volts down to 3.3 volts so that you can use it to power other chips that might be on this module. So we've got a few design requirements here, okay? We have to take in 5 volts and data over a USB connector. We have to then output 5 volts through that same bus voltage, as well as 3v3 coming from the CP2102. And then we have to output RX and TX. One of the big reliability problems with these little modules is that they have 0 ESD protection on them. I've shorted out plenty of these on accident, and unfortunately they just don't have much withstand voltage to them, and it ends up breaking the module. So we're going to add some ESD protection onto our custom board. So in order to do that, we need to lengthen this module out a little bit to make room for some TVS diodes. We'll place those TVS diodes on this particular custom board that we're going to build, then we'll be done. So let's hop into Altium Designer and get started. So I'm in Altium Designer and I've created a new project. You can see I've applied a sheet template. I still have some project parameters I need to assign, and we need to place all of our components. But before we do all of that, I want to jump into the CP2102 datasheet. In the datasheet, we want to look first at the pin descriptions. And of course, you can reverse engineer a lot of this if you have a module that already uses this chip. But what we want to do is go down here to the pin descriptions. First, which pin description do we care about first? Well, first we care about the V-bus voltage. We see that this is a 5-volt input signal from the USB connection. It says it right here in the pin description. Then we're also going to connect that bus input to the regulator input pin. So pins 7 and 8 need to be bridged together. So this is our 5-volt regulator input. Here, VDD, this can be either an input or an output. So this chip could technically run on 3v3. But it will also output 3v3. So I think that's kind of important because we actually want to look at the power diagram on page 19. So on page 19, you can see here that we've got our bus and reg-in inputs together. They're tied together onto the same net, and then we've got a couple capacitors here for decoupling and bypassing. We have an output here that has 2 capacitors, and then it also powers the rest of the device. So you could run this with just a 3v3 input and an external regulator, or you can run this with the 5-volt input. So I think that's an important point to note. The other pins that we need here are just the RX and TX. And then there are some additional pins that can put this into suspend or that can indicate whether it's in the suspend or live state. If you want to hook those up into your own module, you can. You don't really need them in order for this to run. So we've identified some of the critical pins here. Now there's one more pin here, which is this VPP pin. So pin number 18. So on pin 18, if we just look here, it says this pin should be left unconnected or tied to VDD, so our 3v3 supply here. So it's unused in the CP2102, but what you can do is make this compatible with 2109 if you just connect this to the VPP programming capacitor. So if you plan to make this dually compatible with 2109, you can do that. We're not going to worry about that in this board. We're actually just going to use the CP2102 only. That's what we need to do. We also have our USB inputs here. We have our TX and our RX for the UART interface, and that's pretty much everything that we need. So we're going to get some components into Altium Designer, and we'll start building this out. I'm going to copy the decoupling and bypass caps that are found here on page 19. I'm just going to use these values. And then, of course, you can always get some guidance just by looking at the application circuit like this. One thing that you'll notice here, again, this is an option here for these suspend outputs. You'll see here that they actually do recommend having TVS diodes on these data lines. So that's actually something that we're going to add. And if you look at one of these modules that you might buy online, you actually won't see any of this here. You won't see any of these TVS diodes that are placed on these lines and on the V-bus connection. And so this is what makes one of these little modules vulnerable to ESD, and it's very important to add these so that you have some ESD protection. And actually it lists it right here under option 3. You want to have avalanche TVS suppression diodes so that you can have some ESD protection. So this is one of the main reasons that these modules keep dying on me, is because they omitted all of this on those boards that you buy online. So let's go ahead and get started. I'm going to start pulling some parts into Altium Designer and follow along as we go through this design. Okay, so I've got the required connections put into this schematic. It doesn't take a lot of circuitry, as you can see. Here you can see I've got my capacitors placed for my voltage connections. I've got my right angle pin header. And then of course I have my USB-A connector here. And then last but not least, you'll see that there's a shell here that we also need to connect for this USB-A connector. And the other pins here are either marked no connect or they're all optional. I've just left them all as no connect for now. Now, there's a couple things that are missing, of course, here. And if we look back in the data sheet, you can see how they've done this to apply ESD protection. Here, we've got to add 3 protection diodes across the USB connector. And one thing that they've done that isn't explicit here, but you can actually tell just by looking at this connector, is that they've taken the shell, or they've taken the shielding on that USB connector, and then they've tied it to ground. We would want to do the same. You can get creative if you want and add in like a ground ring, but in this particular case, we're just going to go with the shell here. And then we're going to apply some TVS diodes across the V-bus line and then these 2 data lines. I've used the manufacturer part search panel to find all of these parts. I'm also going to look for a 0402 package TVS diode. We've got one from Semtech. It is automotive grade. So we're going to go ahead and for now add this one in. Since it is in a standard package, we could of course change it later. You can see it's got a very large symbol here, but that's okay. We're just going to go with it. We'll go ahead and place 3 of these, and then we'll clean this up just a little bit so that it's much clearer. But with these 3 diodes, we're going to have everything that we need to ensure that we get the proper ESD protection. So one thing I like to do when I have a schematic that looks like this, where I've got these, big labels here, is to, of course, hide whatever this comment is. Sometimes it also helps to actually maybe move some of this down, cut this one, move it down, and then this one we can just bring down as well and go ahead and cut it and paste it. And so these are going to be our 3 TVS diodes. And these are all going to connect back to our ground net on this bottom side. And now we've got them all wired up. So the last thing I'm going to do is force annotate the schematics so that it renumbers the designators. I usually just use annotate schematics quietly. So just click it. You'll see it says there are 3 designators requiring update. Just click yes, and it automatically renumbers these. So these are our schematics. We're basically done with all of this, and we can now move on to the PCB layout. So I'm just gonna add a new PCB to the project. Here, what we wanna do is, of course, set the board size, and we're gonna save this as our PCB. So now we have a saved file. And then we wanna import the board changes. So here, when we do the import changes, we're gonna validate, just make sure everything is error-free, execute, and there we go. We've got all of our components in the PCB layout. Now, we want to set the board size. Setting the board size, obviously, you guys have seen how I like to do it. I just like to use the rectangle and then change the board size definition to match whatever I've drawn in the layout. So I'm going to do that here. The board size of the original module, it's about 5/8 of an inch by 1 inch. I want to make mine just a little bit longer so that we can fit those TVS diodes on there near the USB connector. Once we do that, we'll have enough room to do the rest of the routing on 2 layers. So we're going to do everything on 2 layers, and we're going to do it at standard thickness. So at 62 mils. So we're going to set this to about 5/8 of an inch by 1.5 inches. So I'm going to leave a little bit of extra room on that long edge. That's going to leave room for the TVS diodes. To do that, again, grab a rectangle. Actually, before you do that, go over here to properties, make sure you snap to the board shape, then use the rectangle. We'll go ahead and select this and just draw it out like this. So my width, as I said, we're going to do 1.5 inches, so that's 1,500 mils, and then we'll do 5/8 of an inch in the height, so that's 625 mils, and then we'll just set the board shape from these objects. And there we go, we've got our board shape. Next thing we're gonna do is set the origin, and then we'll go ahead and start arranging the components. So with the component placement, there are a couple of things that we have to keep in mind. We need to keep in mind the fact that our USB connector has to sit somewhere along the PCB edge. And so they've actually done a really good job of indicating where exactly the PCB edge needs to be. And so if you leave the grid set as I've already set it by default, you'll actually be able to align that line right along the PCB edge as I've done here. Now this connector, you can see here, it's not centered vertically. The Y coordinate is pretty simple, right? It's just 625 mils divided by 2. So it's at 312.5 mils, and that's gonna be our vertical offset for this component. And then we'll wanna do the same for the pin header. So that way we have a nice, clean looking layout. The pin header, we're gonna set it just a little bit back from the edge. We'll do the same thing here. So you can see it's already set up very close to the required 312.5 mils. So those are our connectors. We want to start placing everything in the layout, and we want to make sure that we orient the pins appropriately to drag in the data as well as the bus connections. Now you can see here already, they're not named properly necessarily for data lines, but you can see right here, we have our data lines coming in right here. The next thing that we want to do is start arranging our capacitors and diodes. We'll just do that, kind of dragging them all as a group, and then I'll start placing them in this area here. So I'm gonna get on that task next. You guys can watch the routing here, and I'll be back with you all in just a moment. So I have my placement finished. I didn't take up as much board space as I thought I was going to. I've even got a little bit of room to spread out some of these components a bit more if I need to. One thing that is important here is, of course, the fact that these differential pairs are part of the USB interface. And so not only are they differential, but they also have reasonably fast edge rate. These being differential pairs, even though this is a short distance, I think it is important to, of course, route them as you would differential pairs, and that means you need to design them to the correct impedance. Because this is a 2-layer board, you have to take the strategy that I talked about in our USB on a 2-layer board video, which is to do this in a coplanar arrangement. So if we go into the layer stack manager, we can then set our board thickness to the required value, which in this case is going to be 62 mils. Once we set our board thickness to 62 mils total thickness, we'll then be able to create an impedance profile. And once we add this impedance profile, what you're going to do is we're going to set a differential coplanar arrangement. And we're going to set the target for USB. And then we want to set a reasonable spacing. Here we've set 5 mil trace gap, 5 mil clearance between the 2 traces as well as to the nearby copper. So if we do that, you can see here we get 9.437 mil width for the traces on our differential pairs. So that's going to be okay, because here for this pad size, we can see that we have plenty of room to put in a 9 mil wide trace. And then going over here to these pads, in fact, I'll just use the selection filter if I just select this pad, you can see here that we're going to be a little bit larger than the actual pad size, but we're definitely not going to break through any clearance issues between pads. So we can route in 9 or 10 mil wide pads into the two data connections on the chip, and we'll be just fine. Then what we'll do is we'll put ground pour on the top layer to provide the ground reference that these lines require. And then to handle VDD, what we can do is we can route those rails on the back layer, and we can do the same with VBus. We could route that on the back layer. However, given that VBus is actually down here on this part of the connector, we can then just route a thick rail if we want to over to this region and then make the connections here, and then route another thick rail on the backside up here to this edge. Probably, I think the optimal solution would actually be to switch these two nets. So if we just save this and close it, we can go back into the schematic. And I think in this case, it actually makes more sense to switch the position of these two nets. So if we put the 5 volt on the bottom on pin 5 and then the 3V3 on pin 1, it's going to be much easier to then route VBus over here to the pin header. So I'm going to do that now. We'll just make that swap here. We'll make this VBus, and then we'll make the other one VDD, and then we'll import it back in, and then that will update the net connections in the PCB layout. So I just do an update, again, disable the room, hit execute, we're good to go. So now you can see it's going to be much easier to just route straight in from the VBus connection down here over to the VBus connection over here. That also means we need to change our silk screen. So I have these silk screen indicators on the top layer to indicate, of course, which voltages and signals are being output from different pins on the pin header. All we need to do is just change this like this. And there we go. We got it at 5V0. I think at this point, we're basically ready to start routing everything. The most critical portion of this in terms of the routing is just going to be this USB line. We've now got our impedance profile set up. We can go into the design rules, and then if we go up here to the differential pairs routing section, what we're going to do is we're going to use an impedance profile for some of these differential pairs. We want to use this on DC90, and we want this to apply to a specific differential pair. And that differential pair where we want to apply it is our data differential pair. So you can see here on the left side of the screen, my differential pair is named data. You can see the positive polarity and the negative polarity right here. We're just going to apply this rule to that differential pair, hit OK, and there we go. So now it's going to automatically apply all of that differential pair rule setting to these two nets, and then we can just route this in. One thing I'm going to do is I'm going to try and straighten this guy out just a little bit, and then that's going to clean up that routing just a touch. So that's going to be beneficial for us. And then, of course, we need to route straight in to these connections here. One thing that we can do is we can bring these TVS diodes just a little bit closer. You'll notice that these two traces are clustered pretty close together. They have a clearance error between them. You could try and adjust them like this on an individual level if you want. One thing that I would probably prefer to do is just to delete these sections and then route this manually. Sometimes you get these little sections left over that just don't look very good, and sometimes you can get it looking better if you just do it manually. In this case, for this short section right here, just going from data P to the connector and data N to the connector, this short section where they're not very close together is actually okay. The reason for that is it is a bit of a large distance between them, but this distance is so short that it's effectively not going to be noticed by the signal as it travels along this section of the trace. So the distance here is only 70 mils. So that's a lot shorter than the critical length for these lines. And so for this particular case, we can just ignore it. And we could even take, these two TVS diodes and then just move them back a little bit. And by doing that, you'll see here, it just makes a quick adjustment on those traces and draws them back here to the pads. We now have an even shorter impedance discontinuity, so we really don't need to worry about this in our board. So now I'm going to go through and finish up the rest of the routing. The two other important lines here are, of course, the TX and RX lines coming off of the UART interface for this chip. These lines are lower speed. They can be routed through vias. We're really not worried about how exactly we route them. I think for us, what we want to do here is just notice that this particular line just comes off and goes to the top pin on this connector. This one comes off, goes to the bottom pin. So we could come off just like this and route these straight over to these pins. And those are our data connections. If we wanted to, we could go to the back layer. That's perfectly acceptable. We don't really need to in this design, but we could go to the back layer if we want to. What we're going to use the back layer for primarily is, of course, to get this VDD across this chip over to this pin. We have to do that because, frankly, that's really the only way to get VDD over there on a 2-layer board. So that's the other strategy we're going to use, and then we're going to fill the rest in with ground on both layers. So the reason we need to do the ground fill on both layers is because, of course, here on the top layer, you can see very clearly that we have a differential channel that is requiring ground pour in order to set the impedance. And then in order to balance the board with the copper on both sides being symmetric, if we do it on the top layer, then we also have to do it on the bottom layer. And that's going to complete the board. So I'm going to do that now, and then we'll get to see the finished product. So I've finished up all of the routing. I've done some silk screen cleanup. I've added some stitching vias, and you can see here for the bus and the VDD, I use some pretty fat rails just in case we want to draw a decent amount of current out of this device. And this is what the layout looks like right now. This is pretty much finished. You can see here I also added some TVS diodes onto these UART signals. And I think for now, we're pretty much done. So what I'm gonna do is, of course, I'm going to add in our regular logos here in this part of the board. And then we're gonna link to a location where you can download these design files in the video description. So make sure to check that out, and you can download these files and start playing with this on your own. All right, thanks everybody for watching this video. Of course, hit that subscribe button, hit that like button, leave your comments and questions in the comments section. And finally, don't forget to call your fabricator, folks.